Hi everyone, I'm recording this video to show you the solution to the sample final exam. Okay, I call it a sample final exam, but actually it's actually the final exam I gave to my students last year. So from this sample final, you will see what kind of the question I gave to my students last year, and this year, I'm covering kind of the same topics, but all the questions will be different. Okay, so let's see the first one. So the first one is induction, and I know you don't like this topic, and this year I decided I don't want to give you any induction question, so you can skip this one. Okay, so there's no question that purposely testing induction in the final exam. I'm not promising you that induction won't be covered in the final, but there won't be a question like this testing only induction because this belongs to linear algebra. Okay, and then the second one. So I gave you an algorithm, and then I want you to figure out the Tn first. And based on your Tn, and then I also ask for a formal proof of the big zeta. Okay, so the first step will be, well, we want to count the number of the primitive steps. So those three, and they are constant time. So 3 primitive steps. And then this is iteration for n rounds. And how about this one? This one is the iteration for n plus 1 rounds. So it is the n plus 1 iteration inside of a n iteration. So it will be n multiplied by n plus 1 here. And after that, inside of the body of the inner loop, there are 3 primitive steps. So this is the reason we have this 3 here. And similarly, we have another iteration for 2n rounds. And then inside of this iteration, we have 2 primitive steps. And then we also have a constant. Okay, so if you want to add everything together, and this is our Tn. So that is O(n) squared and plus 3n, and then plus a 4. So this is Tn. So from this Tn, and then we need to figure out the upper bound and the lower bound of this Tn. So for the upper bound, well, I'm selecting this n, and then I try to find an upper bound of this n, that is n squared. And then for this one, this 4, the upper bound will be 4n squared. So in this case, I can say this Tn is guaranteed to be smaller than 14n squared. Okay, and then this 14 will be the constant. And plus, I have to specify an n0 as a start point. So here I'm picking the 1. So to prove that it is the upper bound, and then I have to talk about 2 things. Number 1, there can be a constant, and number 2, there can be a n0. Okay, so in here, I still use the idea of the induction a little bit. I didn't prove that, but I'm assuming that we all know that is n squared is greater than n when n is greater than 1. And n squared is greater than 1 when n is greater than 1. And that is the reason that I select here, and I also select here. Okay, so this is the idea that I borrow from the induction, and I know we should be able to prove that, but I just assume that everyone knows it. So this is how I find the upper bound. So how about the lower bound? So for the lower bound, and then I try to drop this part, and then I also drop this n, and then I say, this Tn is guaranteed to be greater than n squared, and also for n greater than 1. So adding those 2 parts, and then I prove that this Tn is O(n) squared. It is also omega n squared. So adding those 2 things together, I can finally prove that this is n0. So remember, when I'm asking for a formal proof of the big zeta, you have to give me the big O and big omega. And for the big O and big omega, you have to tell me what is the constant value here, which is a c, and what is the n0 value here. So after you prove that it is both O(n) squared and it is also omega n squared, and then it is zeta n squared. Okay, so this is for the second question. So the next question. Solve this recursion below, and then you can choose anything, any mechanism you learn from this course. So, well, this one, my observation is this is doable using the master theorem. So once this question is doable using the master theorem, and I will say, okay, master theorem, well, it saves a lot of writing time. So for the master theorem, and remember, you have to figure out what is A, what is B, and what is the Fn. So, well, after you have that, and then you have to do a n powers log BA. So n powers log BA versus the Fn, and which one is higher. And then you can drop this case into the case 1, case 2, or case 3. And remember, if you're in case 3, there's also one more step you have to prove to use case 3. Okay, so in this case, this is case 1 because n powers log BA. So log BA is going to be log 26. So for the log 26, I don't know what the exact value of that, but I have the feeling that it is definitely higher than 1, and actually it is also higher than 2. So n powers log BA is going to be faster than n, so this will put us into the case 1. So this, well, it will be a n powers log BA algorithm. Okay, so the next one, I say you have to use substitution. So for the substitution, and well, the layout will be, well, I do the calculation on the left side, and then I have a small recursion, a small recursive Tn I have to solve. I'm going to solve that on the right side. And then after I solve the small part of the Tn, I'm going to substitute on the left side. So left side will be my main working space, and the right side will be my scratching part. So eventually, well, you have to figure out a pattern like this. So once you figure out such a pattern, and then you can stop. And then you have to say, okay, what if this t inside of the parentheses of the t, what if this value is small enough? What if it is 1? And then we stop this recursion, right? So once we stop this recursion, and then what will be the k value? The k value is going to be log 3n, and then we want to substitute this the k here and the k here using the log 3n. So we are going to have a non-recursive Tn. Okay, so this is for solving a recursion using the substitution. So the next one, well, we have a we are in the process of building a heap. So this heap is not ready yet, and then I want to show you. I want to ask you to show, well, the first 3 heapifies. Okay. So, well, when we have an array as a heap, and then in the process of building the heap, and then where do we do the first 3 heapifies? So for the first 3 heapifies, we have to find the first 3 non-leaf nodes from the right side to the left side. So, well, the first non, well, if we try to visit all the nodes from in the array from the tail to the head. So this is a leaf, this is a leaf, and this 31 a leaf, 51 a leaf, 46 a leaf, and 16 a leaf. And then we have the 13. So 13 is the first non-leaf node. So we are going to do the first heapify on the node 13. So after we have done the first heapify on the 13, and then we are going to move to the left side. So we are going to do a heapify of the 10 and heapify of the 31. So after that, and this will be the heap, the unfinished heap. After 3 heapifies, we are done. Okay? So in the next one, we are doing a partition on a quick sort. So for the partition, well, we are assuming that we are using the first value as a pivot, and then we have 2 cursors. So the left cursor starts from the second value on the left side, and then the right cursor starts from all the way to the end. So we have 2 cursors, and what are we finding? We are trying to find the 2 values. They are both on the right side. So on the right cursor, I find 2. So 2 is smaller than the pivot. So 2 should be on the left side. And then I also have the 7. 7 is larger than the pivot. So 7 should go to the right side. So now I find 2 values, and then they are both on the right side because the right value is small, and then the left value is larger than the pivot, so they are going to be swapped. So once we swap the 7 and the 2, and the next round we are going to move the cursor inside, and then we try to find another pair of the values. So we will keep on doing so until those two cursors have already crossed. So once those two cursors are already crossed, and what's the next step? The next step is we want to swap the red cursor value to the pivot. So this 1 will be here, and this 4 will be swapped to here. So this will be the final version. Okay, the next one. Well, among all the comparisons based sorting, which one has the best case big O? Okay, so we are talking about the best case. So, well, you may assume that the best case is, well, the list is pre-sorted, right? So when a list is pre-sorted, and you may assume all the algorithms should be faster, but it is not true. And think about that. If you remember the quicksort, if we have a pre-sorted list into the quicksort, what is going to happen? If we are picking the first value to be the pivot, and then there will be 0 value on the left side and all the values will be on the right side. So a pre-sorted list into the quicksort, that is actually the worst case. So which one has the best case? And well, it is interesting to find that insertion sort, that is the winner. And do you remember the insertion sort? So it is one of the first algorithms we introduced, and then well, I use a set of the cards, right? So well, I have a sorted portion, and then every time I want to expand the sorted portion by inserting one of the new value into the sorted portion. So if the new value to be inserted into the sorted portion is actually larger than any value in the sorted portion, and what do? We should include that into the sorted portion, but there's no value to be swapped. So this makes the best case linear for the insertion sort. So insertion sort, that's the right answer. So the next one, well, recursion. So for the recursion, here's the question. We have a sequence of letters or numbers. Well, it will be a string. So like the 1, 3, and 5. And then I'm asking you to write a recursive increasing sequence checker that takes a string and then tell me true or false on whether this is an increasing sequence or not. So, and then how do we do that recursively? So one of my idea is, well, how about every time when we take a sequence, if this sequence has 0 or 1 character, I'm going to give a true. And then otherwise, if this sequence has more than 2 characters, and then what I'm going to do is I'm only going to try to check the first 2. So I'm only going to check the 1 and 3. So if 3 is higher than 1, this means on the first 2 values, at least there is a promise that it can be an increasing sequence. And what is the next part? The next part is, well, I've checked the first two characters, and they are in the increasing order. So now I'm gonna skip this one, and then I'm gonna do a recursive call, and after removing the 1, I'm only checking the remaining n-1 characters. So in this case, I'm only going to check the 3 and 5 because this 1 and 3 is safe. So I'm erasing this one, and I'm only checking all the rest of the characters after deleting the first character. So this is my recursive solution. So the next one, topological search. So well, given the graph is at a DAG, well, how do we check if it is DAG? So is this directed? That is the D, right? And it is yes. Well, do we have any circles? Well, I mean, following the directions of all the edges, can we go a circle and then come back to where we are? The answer is no. Well, you may say 2, 4, 5, and 7. Is that a circle? The answer is no, because 2 can go to 4, 4 can go to 7, but 7 cannot go back to 5, and 5 cannot go back to 2. So there's no circle here. So well, the answer is, for the first question, is that a DAG? And the answer is yes. And the next part, we want to do a topological sorting. And then when we are doing a topological sorting, and then the process is going to be, we do a depth first search, and then for the nodes we finish, we want to write this sequence from the bottom up. Okay, so start from the 0 and start time is 1, and then to the node 2, start time is 2. And then we go to 3, the start time is 3, and then we have the 6, and the start time is 4. And then from 6, we can go nowhere. So we say, okay, 6, you are finished. So once we say that 6 is finished, I'm gonna write the 6 here, and then I step back. So after I step back to 3, and then, well, 3 is finished too. So I write the 3 here. So when I write down those values, I write them from the bottom to the top. And after I finish this sequence of the DFS, and then all the nodes from the top down, and that will be the result of a topological sort. Okay? So the next one, the BST. Well, this is the interesting question. And if we have the two trees, two BSTs, and how do we know if those two BSTs, they have exactly the same values? Well, say for this one and this one, they are both valid BSTs. But how do we check if they have the same values? Well, one of the idea I have is, do you remember for the BST, we can use that as a sorting algorithm. And if we want to use that as a sorting algorithm, what do? We just do a in-order tree walk. So after we do an in-order tree walk, we put all the values into an array. Well, and this array has all the tree values from low to high. Okay, so if I do a tree walk on the left tree, and if I do another tree walk on the right tree, and now I will have two arrays of the tree values. What's the next step? The next step will be, I have two arrays of the tree values. I only need to check if all the values are exactly the same or not. So this will be my idea. But this question has a lot of the different solutions. So the next one, RB tree. So for the RB tree, we are trying to insert 60 and 17. So for the 60 goes here, and 60 will be a red. So once this 60 is inserted here as a red value, do we break any of the RB tree property? The answer is no. So we are safe. But the next one is going to be tricky. So we have the 17. So 17 will be inserted here. So what we are going to have will be, we have the 20. Okay, let me make it bolder. So we have the 20. And then on the left side, we have a 16. But this 16 is going to be a red value. And then we have a 17. This 17 is going to be a red value again. Okay, so in this case, do we violate any of the RB tree property? And the answer is yes, because we have two red nodes next to each other. So how do we fix that? Well, the process will be, first we want to do a rotation. We want to do a 20 and then a red 17 and then a red 16. So this will be the first step. We want to put those two, 17 and 16, in the reverse order, so they are in one line. And then we want to do a rotation, and this will give me the 17, and then on the right side we have the 16, and on the right side we have 20. And then we are going to have the 17 to be a black, and then 16 will be red, and 20 will be red. So this is how do we fix a RB tree. Okay, so the next question, the MST. So for the MST, and we want to do a Prim's algorithm. So this Prim's algorithm is going to be super long, and I only ask for, what did I do? Okay, here we go. So for this Prim's algorithm, and then I'm asking for the key and pi after we have extracted the 1 from the priority queue. Okay, so this process is going to be super long. So I'm going to try to show you my way of doing that. So this is my scratching process. So I started from the node 7. So when this node 7 is included in my BST, and then I'm updating the values on those nodes and showing if it is accessible if it is accessible based on the nodes already in my BST. And then if this node, for example, this node is not accessible yet, I'm going to have a infinity. And for this one, and we know this node can be accessed from the 7 by 1. So I'm writing a 1 here, saying the cost of including this node to the BST is going to be a 1. And so similarly, for this one, for this node, and the cost of including this node is going to be a 7 and 11 here and 8 here. Okay, so based from here, well, based on the values we have written on the nodes, which one has the lowest value? And we have the 1, right? So the next time when we do a extract mean, we are going to extract this node, and now this node is going to be in our MST. So once this node is in our MST, and remember, well, we used to have a 7 here, but because the cost of this edge is a 6, this means if we want to include this node into my BST, now the cost is going to be a 6. So I updated this value here, and also this value becomes accessible and the cost will be a 2. So on this version, if we want to extract the mean from all the nodes that we have the numbers, but they are not circled yet, and then I'm going to extract this 2. So the next step, I want to extract this 2, and now this 2 is also circled, saying this 2 is also part of my MST. So once this 2 is my MST, and then, well, this node becomes accessible, and then the cost is going to be a 10. And for this node, well, because this node is accessible, so, well, we can also include this node, and the cost will be a 4. So now, for our candidates, we have the 8, 11, 3, 6, 4, and 10. So if you want to extract the mean, it's going to be this 3. So we want to extract this 3. So after we have this 3, and then, well, here, well, this node used to have a 11, but now since this 3 is also part of the BST, it's also part of the MST, and then, well, we can include this node using the cost of 8. So I'm updating this value here, and, well, we used to have a 4 here, but from here to here we have a 5. So this cost is even higher than 4, so I'm not going to update this value. So after including this 3, now for the candidates we have the 8, 8, 4, and 10. So we extract the mean, so this means we are going to extract this 4. So once we have this 4 included in the MST, now, well, we used to have a 10 here, but now because this 4 is in the MST, so now I'm going to update this value to 9. So what are the candidates we have? 8, 8, and 9, right? So we have a tie. Okay, so in this case, and which one are we going to extract first? So remember, the rule is here. When there is a tie, visit the nodes with the lower number. So we have the node 0 and node 1. So we are going to extract this 8 first. So we extract this 8, and then, well, we have a, from this 8 to this 8, we have a 14. This 14 is higher than 8, so nothing to be extracted. And then we are going to finally extract this value. So after extracting this, and we find there's nothing to change, so this is how where we stop. Because it says, well, you want to stop after the round when the node 1 is extracted as the mean. So this is the stop point. Okay, so we have to extract this node, and then we extract this node, and here is where we stop. Okay, so the next one, we are doing the Kruskal. So for the Kruskal, and well, we want to stop after we have visited the 10th edge. So if you want to take another look on the Kruskal algorithm, and we are visiting all the edges from the lowest value to the highest value. So, well, in this, for the edge between 7 and 6, the cost is 1. So we are going to visit this edge first. But there are some other things we have to do. So how do we break the ties again? So here are the rules. So if we write down, if we want to write down a edge, we want to put the lower value first. So we want to say the 0, 10, 07 as a edge, well, we have to name it 07 instead of 70. Okay, so we want to name it 07. Well, this is the first thing. Well, once we have a tie, and then for example 28 and 56, that is a tie, and then the tie break will be, well, on the first value, which one is small. If the first value is the same, and then on the second value, which one is small. So which one is smaller goes first. And this will guarantee that 28 will be visited before 56. Because the costs are both 2, but 2 is lower than 5, so we are going to visit the 28 first, and then 56. So in the cruise call, and we started to consider all the nodes to be in a different set. And then when we visit the edges one by one, from the lowest to the highest. And then for each of the edge, it will be two possibilities. If those two nodes connected by this edge, they are not in the same set, and then we want to merge them together in one set. So for example, 6 to 7 connected by 1. This 6 and 7, they are in separate sets. So now I'm going to take this edge, and then I'm going to combine the 6 and 7 into one set. Okay, and then also the 2, 8. 2, 8 used to be in two separate sets. Now they are combined. And 5, 6, again, they are combined. So it will also be something like this. So this will be the second case. 2, 7. Sorry, 2, 3. So for the 2, 3, and the cost is 5. So for this 2 and 3, are we going to take this edge? The answer is no, because if you check the 2 and the 3, they are already in the same set. So it doesn't make sense to include the edge of the 2 and 3, because this 2 and 3, they are already together in one set. So in this case, I'm still going to visit this edge, but I'm going to cross this out and saying, okay, this is the edge. I'm visiting that I'm visiting this as the number 6 edge I'm visiting, but I'm not going to do anything. Okay, so after you stop at the 10th edge, and you will find that the only node that is still as an orphan in a separate set will be the node 4. So the next one, well, in the Dexter's algorithm, well, we have a min heap to handle the priority queue. Okay, because every time we want to extract the mean, and when we extract the mean from the priority queue, from a min heap, what do? We grab the top value, right? And then we fix the heap. Well, and I have a funny idea. How about we use the arbitrary as a priority queue instead of a min heap? And then, well, there are some of the hidden costs we have to pay. So for example, when we are trying to do a extract the mean, so we are taking one of the value out from the priority queue, and this priority queue is done by an arbitrary. So we are taking one of the value out. So there are two things. Number one, we are taking one of the value out. Well, this is we are grabbing a node from the arbitrary. And number two, once we have taken out a node from the arbitrary, and then we have to fix the arbitrary, right? So there could be some extra cost. So what is the extra cost? And then you have to tell me about this, because on this part, it's guaranteed that, for this part, this iteration will be run for OV time, guaranteed. But what is the hidden cost? And you have to consider the property of the arbitrary and the cost of fixing an arbitrary, and then you have to fill in this value. So, and this part, this question mark is going to be a log v. And for this part, we are visiting all the edges. When we are visiting all the edges, and then it will be a OE guaranteed. And then what do? We want to update some of the values in the priority queue. Once we update some of the priorities in the priority queue, and then some of the nodes should be swapped. So for example, say I have 10 here, and then, well, we have a min heap. Well, if we have an arbitrary, and then we have a 10, and then on the left side we have a 5, on the right side we have a 11. Okay, so how about this value got updated? Now instead of a 11, this one becomes a 9. Okay, now there's a problem because this is not an arbitrary anymore, because an arbitrary has to be a binary search tree. And then, well, this is not a binary search tree anymore, so we have to fix this tree. So what we can do is we can delete this node, and then we want to do a insertion of the 9 again, so that this 9 is inserted into the right location of this arbitrary, and then we have to fix the tree again. So what will be the cost? This question mark is going to be a log v. So in this case, well, we have to use our understanding of the arbitrary to figure out what are the hidden costs of using an arbitrary as a priority queue. So this question is going to be the hardest question you see. Okay. Well, this is just to give you some of the idea on what are the questions that I'm likely to give you, and well. What I can say about the final exam is, well, you are not going to see any of the same questions in your final exam. It's not going to happen. But I'm going to try to give you some of the tests, some of the tastes on what are the questions you are likely to see. Okay, so for those questions, and I would say if you have reasonable understanding about the course material, it will be doable in, well, 3 hours. And another thing I want to remind you is, well, try to do better in the plots. Well, for this set of the answers, well, I did this answer for my own reference, so I didn't pay attention, and some of the handwritings are not accessible. So you have in my solution, I would still say some of my handwritings are not accessible. So that's the reason I say, well, you have to type your solutions. If you just do what I have been doing on a scratching pad, and if your handwriting is so not readable enough, well, you may receive a 0. So, well, try to spend some extra time to type your solutions. Okay, so good luck for your final exam, and let me know if you have any questions. Bye-bye.